Hey Data Junkies, welcome back to another episode of Multiple Linear Regression with your host, Shawn Janzen. We're continuing our adventure today and to the topic of multicollinearity. Multicollinearity is an issue that happens when your independent variables start predicting each other a little too much. They're getting a little too friendly, a little too cozy. And this is actually one of the regression assumptions we faced earlier that we started to hint at and introduce in simple linear regression that we're now going to be able to expand upon and see just what sorts of trouble does it cause and why did we have to wait until multiple linear regression in order to face it. Well, just to cut to the chase, the reason we had to wait to multiple linear regressions instead of simple is because you needed to have more than one independent variable to work with. Simple regression only had one, therefore it couldn't happen, it couldn't work. Whereas with multiple linear regression, we have, of course, two or more independent variables, and multicollinearity is happening when your predictor variables are overly correlated with each other. Now, you're going to have some correlation between them. This is normal, this is usual. And having small amounts of correlation, not so bad. We can live with that. We can work with that. Moderate correlation, this can start to affect your regression in meaningful ways. And at high amounts of correlation, then we have a technical term. We say that your model's blown up. Okay, it has perfect redundancy with one or more variables and can damage your model. So 3 different ways that you can introduce multicollinearity into your regression model. First of all is improper dummy coding. In the previous videos, we talked about how to use dummy variables, and one of the things that you had to learn was k-1, where 1 was the regression group, the reference group, that one categorical group that you leave out that serves as the comparison between it and the other dummy variables. Now, if you were to just put in k instead of k-1, meaning you didn't leave out a reference group, then congratulations, you've just introduced multicollinearity into your particular regression model. Another way that you can do it is by including an independent variable that's been computed, that's been made, constructed from other independent variables that you have. Think of it as one of the examples we're going to have here soon enough, where we're going to be measuring out body fat and looking at the different predictors of it. When we first started with that example back in correlation, we built a variable called BMI, body mass index, and it was built from measures of height and weight. Those two variables there, height and weight, made BMI that we then could check with body fat, other issues. And height and or weight are both going to be highly correlated with BMI. If we were to include BMI and then either height and or weight into a regression model, congratulations, we've just introduced multicollinearity. Another way that we could do it is using one or more independent variables that estimate the similar or even same measure to each other. Think of it as a situation where you might be measuring something in both miles and kilometers, and you put both measures of distance into your regression model. Congratulations, you've just introduced multicollinearity. Now, depending on how you're dealing with your data and building out some new variables, you might have 2 and 3 overlap quite a bit. By creating new variables from other data in your data set, there's the possibility they could be measuring similar sorts of things, which is where 2 and 3 can overlap. Now, what happens? What is this big specter of multicollinearity? Why should we be worried about it? Why should we be afraid of it? So, first of all, when it comes to your estimators, your betas, those are going to be okay for the most part. Right? We have other issues like outliers that can damage those, but multicollinearity, that tends to leave your estimators alone. What it tends to do otherwise is mess with your standard errors. Okay, having this a large amount of variance issues in your regression gets larger, the covariances go up, so that leads to differences in your standard errors. That causes smaller t-scores. Remember that the t-scores are the result of having your standard errors divided into your regression coefficients. If your standard errors are off, it can throw your t-scores off. It throws your t-scores off, your confidence intervals can be wider, it can cause larger p-values, which could then lead to not rejecting the null hypothesis as often as you should, and therefore you are going to be generating more type 1 errors. So, a downward spiral, toxic effect, and just something that we can hopefully avoid in the first place, okay? Now, how can you see it? How can you know it? How can we avoid it? Well, if the estimators are unbiased, that's going to be okay. We're not going to see it there. But because the estimations are going to be difficult, where else can we look in our regression model where we're looking to see when we're talking about doing precise estimates? Well, keep in mind R squared. R squared was a measure in which we were talking about the definition of it was the amount of variation in the DV accounted for in the IV. It's a perfect little number that's talking about explaining variation. Now, when you've got too much variation being explained between your variables as well, it can help drive R squared up. It inflates itself higher than what it needs to be. And so you can start to recognize some of it there. So let's go ahead and see what some of this looks like coming off. We're looking at an example with body fat, and I'm reading it into the data as a data set called BF. I'm turning on the performance analytics library so I can get access to a chart.correlation function. So you have the chart.correlation function on the body fat data, and we're selecting variables called body fat, weight, chest, abdomen, hip, thigh, biceps. I'm also going to save these variables as a regression model object that I'm calling lm.bf that we can use later on when we want to do some of our analysis. So on the screen, we have a large correlation matrix, and this is our first case chance to see, could we find multicollinearity? Keeping in mind that multicollinearity is when our independent variables are overly predicted with each other. Correlation matrices are a great place to start. Now, it's okay and it's even great if our independent variables are correlated with our dependent variable. But we're not worried so much at looking at that part right now. We're looking at independent to independent. Now, in this particular correlation matrix, it may be a little hard due to the number of them that I have based on the size of the slide and squeezing them all in, but in the upper left corner, up in the tip top, we have body fat. And so we have the histogram of body fat, and all of the correlations to the right of it are the correlations of the independent variables with body fat, as well as with the scatter plots going down below it. And then going down on the diagonal, we have weight, chest, abdomen, hip, thigh, and biceps. So we can then look at the different correlations between any of those. And keeping in mind with the chart.correlation that we have here, we're getting asterisks in the regression coefficients. Sorry, not regression coefficients, correlation coefficients. So we can see which ones are certainly statistically significant from each other. And a lot of them are in these numbers of like above correlations of 0.8, 0.9, 0.7, a couple 0.6s in there, but quite a few of them are very high. There's a lot of high correlation going on with each other. And we can see that as well on the lower half of the chart where they have the scatter plot matrices. Some of them are really tightening up to each other. So this is one way to get a quick visual, but it's not going to give us something that's overly precise per se if we want to get exact measurements. So let's go a little bit farther. Here's another metric. It's called tolerance. Tolerance is another quick eyeball check. It's the potential for multicollinearity to come into play. So tolerance is just 1 minus r squared. So you can think of it as the opposite of the coefficient of determination. And our first threshold for tolerance in the entire model is 0.10. That's the common amount. So if your r squared is 90 or above, 0.9 or above, then it's going to be triggering your tolerance, and you could have multicollinearity. At the very least, the highest tolerance you should tolerate should be a 0.2. 0.2 means that you've got an r squared of 0.8 or above, and that's where you really start needing to worry. Now, if we want to get even more precise, let's talk about VIF, or VIF. That's short for Variance Inflation Factor. The VIF score is a number that's going to tell you in that particular variable how much of that variable is inflating the variance into your model. How much of it is due to multicollinearity here. The higher the VIF score on a variable, the less reliable it's going to be in your regression model. And the VIF score is calculated by 1 over 1 minus r squared sub j, where j is a particular predictor variable. It's an inverse of tolerance, but we can use it for each individual variable. Now, how do we get this in R? Super easy. We need the car library, and once you get the car library, then all we need is a function VIF. Inside VIF, you can write your regression model, or if you have your regression model as a saved object, which I did earlier, then we can put that inside of the VIF. Now, if you can't get access to the car library and or you're having problems with the VIF scores, I did include in the lecture script a few extra functions that are buried into the script on eigenfunctions. So check those out or come see me, and I'll show you other ways that are a little less simple and straightforward as using a VIF score, but can certainly help you track out the multicollinearity here. Now, coming back to the VIF scores, if it's going to give you a number, that number is going to help you figure out if you've got multicollinearity or not. We need to know what numbers you need. So anytime you're getting a VIF score, they typically start at round 1. And if you're going from 1 up to 4, everything is fine. Nothing to worry about. 5 is where you draw the line in the sand. We don't want to be above 4. 4 is your maximum happy zone. 5, that's the line in the sand. 10 and above, you have serious, massive multicollinearity issues going on. Your model could be blowing up, and things just aren't going to be working out for you. Now, where does some of these numbers come from? Why are we using 4 as our baseline of, I don't really want to be any closer than past 4, and 5, why do we not go there? Well, a VIF score of 4 means that the standard errors you have are twice as large as they need to be when they're going to build their confidence intervals. All right, so you can think of it, if your confidence intervals is twice as large as they need to be, that's definitely causing you some problems there, and that's starting with that VIF of 4. So if we can keep it under 4, we're going to be doing much better. Now, let's go ahead and use that body fat measure that we had with the 6 predictor variables onto body fat, and I'm plugging them into the VIF score, and I'm going to go ahead and do a round on the VIF score, and I'm also just doing that to kind of clean up the results here, and I'm putting them onto the screen. So when you print these out, they normally just print out all of your variables in a row, kind of like as if you did a table function. So that when I'm portraying them here on the slides, it's pretty much the same results. I've just put it into 2 rows of output instead of 1. So here we can see that we have each of the 6 variables and 6 VIF scores, 1 for each. Weight has a VIF of 16, chest of 8.7, abdomen 8.556, hip of 13, thigh of 6, biceps of 3.136. Do we have any problems here? I'd say we do. Take a look at weight and hip. Both of them are above 10. Major problems here. Are there any others that are past our threshold of 5? Absolutely. Chest, abdomen, and thigh are all causing problems here. And chances are some of those VIF scores could be going up based on some of those that are higher than they need to be. Another way we can look at this is, instead of looking at the VIF scores for each individual variable, we can also take a mean of the VIF function of the regression model, and that's going to give us the VIF of the entire model as a whole. Now in this case, you don't want to be above 2. 1 to 2 is, you don't want to be higher than that. Don't go above 2. The mean VIF score of our model at the moment, 9.25 and change. So definitely showing that we have a problem here. Now, once you identify multicollinearity, what do you do about it? How do you get it out of your model? Well, we do have a few things and options in play. The primary method that we're going to show you, or I'm going to show you in the video today, is what we call a stepwise selection strategy. Now, the way this one works in particular is you start with the highest VIF score in your model, and you kick the variable out. Rerun your regression model, check your VIF scores again. If you still have some offenders, kick out the next highest one. Rerun your model, check the VIF scores again. Rinse and repeat until you finally get your variables down to a point in which you're no longer violating multicollinearity. Now, this isn't always the best approach, because you may be kicking out variables that are important to your model for theoretical reasons and other practical reasons, or maybe you want to find some that You'll remove that are no longer the highest indicators, but other words. So we need to take this on a case by case, but this is one of the tried and true methods that's just going to go through and drive down your model variables until you get your VIF scores under control. So looking at the body fat predictor variable where we have our 6 up here, I have a table filled out at the moment, and we have the 6 VIF scores that we had from above. Using our stepwise selection strategy, I'm going to go ahead and drop weight. Weight had a VIF score of 16.0. Dropping weight, rerunning my model, rerunning the VIF scores I have up in the table now that we have. Are we still over 10? No, we're not over 10, but we're still over 5. That line in the sand, 5. I have 4 out of my 5 variables have VIF scores over 5. Definitely still a problem. My next highest one was hip, so I'm going to go ahead and drop hip, rerun my regression model without it, recheck my VIF scores. Now I still have 2 of them with VIFs above 7, and then the other 2 are in the safe zone below 4. Now at this point, chest and abdomen are almost identical to each other in terms of their VIF scores, but just for the sake of using the absolute largest number, I'm going to go ahead and drop abdomen. When I drop abdomen, rerun my regression model, and check my VIF scores again, congratulations, we are now with 3 variables, all with VIFs under 4. And so multicollinearity is no longer a problem in my model. Now keep in mind, I've had to choose certain variables that may or may not have been the best predictors for what I'm dealing with. When we were dealing with the correlations before, we saw that abdomen had the strongest correlations. I think this was the simple regression examples, not correlation specifically. Abdomen was the strongest predictor of body fat when we were doing these different metrics, but we had to drop it here because of its relationships with the other independent variables. What we could do is possibly put abdomen back in and try dropping other ones in its place if we think that abdomen was more important, and see how it works. Check for that multicollinearity issues. Now, is it okay to just leave the multicollinearity alone? Well, like we said before, it's a downward spiral into type 2 error land here. So it's never that it's okay. It's more of a question of, is it tolerable? So if you have high VIF scores from control independent variables, these are the ones that are not your primary ones of interest. These are variables that you're putting into your model to simply help explain variance. A lot of times these deals with demographics and other particular variables that are, like I said, not the ones that you're particularly focused on for the explanations of the research questions you have. So if you have high VIFs due to them and not in your primaries, it might be okay to live with. If you're getting high VIF scores due to some of your independent variables that have been raised to powers or products with each other, we're going to talk about this when we get to the sections on interactions and polynomials. These can have higher VIF scores because one of the ways you can introduce multicollinearity is to build variables in your model that are based off of other variables in your model. And so it's natural to have these with interactions and polynomials. So in this case, you're definitely going to be more likely to introduce it in. So the question is, how bad is it? Can you tolerate it? Now, if you have p-values that are really low, you're looking good, you don't have to worry so much about having standard errors running away from you, then you can go ahead and keep your interactions and polynomials and other variables like that that have these construct effects that have high VIF scores. If it becomes questionable, though, with your p-values and you're not sure where it's going, then we need to take that double consideration of, do I need to back this off? And the last one was the dummy variables with the reference groups. Now, if you're getting high VIF scores because you don't have a reference group at all and you've plugged in every dummy you could, then that's a problem and we need to fix it. But if it's an issue that can also arise by choosing a reference group that has a relatively small frequency count in that reference group relative to the size of the other dummy variables in the model. I was saying before that one of the selection strategies here was to choose a dummy reference group that has a larger frequency count. That will help offset the problem here that we have of having the small reference group count. So keep some of that in mind. The sizes there can mess with some of the standard errors when they're making those comparisons. Now, if we could go ahead and fix it, why don't we just fix it? I was saying before that checking things like your standard errors and your p-values, that's what's getting messed with when you're introducing multicollinearity. So if you've got really rock star p-values and standard errors, you can have that little bit of inflation going on there, and it might not be so bad. By going ahead to do that, then you're making it easy on yourself. You're keeping things oftentimes simpler to explain, helps with your interpretation, your model's still behaving nicely. Another way that we said before is you may have good quote-unquote reasons to keep the offending variables in there. This gets back to the case when I was talking about the abdomen with the body fat. That might have been your best predictor. You may have some logical reason. Others that have been doing research have kept it in. There's a host of reasons in which we can rely on theory and previous research to help inform our current research that we may want to consider what's in or out of our model based on how bad the multicollinearity is. Okay, so keep these things in mind as you're moving forward, and that's going to go ahead and wrap up our talk on multicollinearity. I'll see you all in the next video when we start talking about model selection. I'll see you then.